All right. So thank you for joining Networkers Jam today's session. So today we are going to discuss basically the CCNP Enterprise Core and Advanced Routing and Switching. This is the first day of the class. My name is Suraj from Networkers Jam. Now, here is the agenda that we will be talking about throughout this session, right? But before agenda, the agenda is on the screen, by the way. We would be talking about architecture, right? We will see the different architecture, like the design principle, right? This is where we talk about the two-tier architecture and what is three-tier architecture, as well as we will see the wireless LAN deployment, right? Because this entire course of CCNP Enterprise Core and Advanced Routing and Switching, or RNSI, right? This would be based on three major, deployments, three major actually track. One is the routing and switching. The second is the wireless, and third is somewhere down the line, the security, right? Moving forward, we will also talk about the basic routing flow and then basic switching flow. So in this basic switching flow, we'll talk about hardware and software switching, the difference between hardware and software switching, like for what is process switching, what is safe, right? What is fast switching, and etc. We would see the step by step. When I say basic routing flow, we'll talk about, step by step packet flow. So that's what basically I I meant here. Um, packet packet flow, which is again very important, from the troubleshooting point of view as well as interview point of view, because most of the time this packet flow is asked, right? In routing and in switching and in overall network as well, right? This is the so in architecture, basically, we would talk about, the first this like we'll talk about the different design principles used in an enterprise network. So this is where we'll talk about different design, tier 2, tier 3, right? What is the fabric capacity planning, how you should go through it, right? All that. So not everything from this architecture one, but this part, and then we'll also talk about this WLAN deployment, right? What is basically centralized, distributed, controlless, or controller based, right? And then also we'll talk about this differentiate hardware and software switching mechanism in today's class. Okay, so let's kick off this class, right? So when it says basically the architecture, it is very important to understand the architecture of any network that you are going to work on, right? So this architecture is completely based on, first of all, the enterprise network. You can have an architecture for enterprise network. You can have an architecture for, WAN, right? So this is purely based on enterprise network, right? Now, as we all know, in enterprise network, what all endpoints or what all devices that you can have, right? So let's make this session also interactive. I am going to ask a lot of questions, you know, from you guys as well. So when I ask, can you tell me the component of enterprise network? What all like resources, component, or accessories or nodes, whatever you say, right? What do you think? If I have to build a network, right? Enterprise network, what do you think? What all you can see in this enterprise network? Anyone?
Routers.
Very,
SD-WAN.
very good. Routers. Yeah. Routers,
Right.
which acts as a more preferably a gateway. What else?
Switch.
Switch.
Switches.
It's, it's
Yes.
work on a MAC address.
Yes, we'll talk about that. What else?
Access
And
point.
Access point from the wireless point of view. Yeah, access point. This is basically for used for wireless. What
And
else?
end devices.
End devices like PC, right?
Yes.
Like servers, printers, IP phones. What else? I mean, there are a lot of, but we are just putting the majorly, right?
Yes.
How about firewalls? Somewhere there would be a firewall also, right? For the security. What else? Wireless controller, we call it actually WLC. Again, this is for wireless, right? Anything else that you can remember? Wires
Then we are using
that
SD-WAN, right, in
that
this line.
wires can be, hold on, please. Yeah, SD-WAN is you can say, because we have the routers, so routers or SD-WAN, it's same, right? So wires as in cables, right? What all cables we use here? We use Ethernet. What else? Fiber optic. Anything else in the cable that we use? Maybe console. Anything else? Then you have the connectors, right? Connectors, RJ45, SFP connectors. We'll talk about all these, right? What are the connectors and all that? How do we use it? But yeah, pretty much if I may have missed, few things here and there, but this basically covers pretty much everything. This is what you're going to see. Rough idea, okay? I mean, you may have a lot of other things definitely based on the deployment, based on the services and all that, but a rough idea, this is what it consists enterprise network, right? Now, in order to basically design, or in order to basically design the enterprise network, these are the two design that you can think of, right? The first design talks about the tier 3, right? Three-tier architecture. Why three-tier architecture? As you see here, we have three layers, consisting three layers here, right? In this three-tier architecture, one is the access layer, the distribution layer, and then the core layer, right? So what is the job of access layer here? Anyone?
Access layer is connect to the end devices.
Right. So access layer basically connects to the end devices. Now, end devices we talked here, right? Talked about PC, servers, printers, IP phones, right? All those end devices you can see in connected through the access layer switch. Now, so what is important in access layer switch? What you should have in access layer switch? You should have the port density. Usually in access layer switch, we have a port density. What does that port density means? Let me just put it here. So port density. Port density basically means the number of ports in access layer switch to connect the end devices, the endpoints. That's what it is actually called, port density. in access layer switch. Okay. Now, because every port of the access layer switch, let's say this is the switch. Okay. I would in this basically switch, what we have, you have here a number of ports, isn't it? These number of ports called port density, and you would see an access layer. Each port would connect to the one device, right? Each port would connect it to one device here. Do you agree?
Yes.
Now, this port density, because they are dedicated connected to a end device, you would see here they have a dedicated bandwidth, right? They have dedicated dedicated link going to end device. Now the access layer switch is purely you can deploy as an not very higher end model when we talk about the cost wise, right? So you, because any switch will, let's say if it has 24 ports for an example, so that means it will connect, let's say 22 endpoint, right? So ultimately this switch is handling 22 endpoints traffic. Do you agree? How many? 22 endpoints. So like that, if each switch is having 24 ports, right? So somewhere 20, why I said 22, because one port will go to one switch, and another port. There will be two to three port, connected here and there. That depends again, but yes. So ultimately, what point I want to make here is every switch has a limited responsibility to handle the traffic, right? But when it goes to, that's what basically access layer. But when it goes to the distribution layer, now you see the distribution layer is sitting in the middle of between core and access layer, right? So ultimately, you see most of the traffic from this are going to the distribution layer switch, right? So in number also, you would see the number of distribution layer switches would be less, right? Why? Because most of the end user traffic will go to the distribution layer switch. Now, this is where you have to plan a higher end, device so that it can handle all the number of users traffic easily. The distribution layer switch is also used for management. Like if you want to create the VLANs and all, where do we create the VLANs in this topology? It is the distribution layer switch. All VLANs would be created to the distribution layer switch. Management, if you're gonna use, if you are also doing the inter VLAN and all, preferably you would do it here, right, at the distribution layer switch, right? This, and important here, that every switch has a high availability also. What is high availability here? High availability. Ability, right? High availability, we call it HA, or we call it sometimes redundancy, anything, redundancy, anything, right? So there are basically high availability or redundancy. There are three types of HA. One is link level HA. Second, hardware level, hardware HA. And third, ISP HA. What does that mean? Link level HA means, do you see anywhere link layer high availability? Anywhere in this picture? Anywhere?
Distribution layer.
Distribution layer, no, I don't see level high availability in distribution layer. But I see in the core layer
Core layer. Yeah.
where this core layer is connected through the two cable. This is the one and this is another, right? That's what it actually called link level availability between these two core layer switch. if this link goes down, the another link is there, to to be operation. That is called link level high HA. What about hardware availability? Yes, we have HA here in distribution layer. If this switch goes down, then this switch will take over the traffic. If this switch goes down, this switch will take over the traffic, right? For certain number of switches. Similarly, if this core goes down, this device goes down, then we have this core as an standby. That is called hardware HA. Third is ISP HA. ISP means if you rely only on one ISP, let's say this is ISP and both the cables are connected like this, what if this ISP there is a power outage and whole ISP is down? Then your entire network is down. So ISP level basically means you will have ISP1 and ISP2, you will have connectivity like this also. So the if basically this ISP is down, you have the another link to go to this ISP. That is how basically we ensure the high availability also, right? Core layer, as you see here, core layer is basically sitting at the edge of your enterprise, right? Where it is connected to the distribution layer and also connected to the, your gateways. Core layer could be your, further gateways, which we call it enterprise edge. What do we call it? Enterprise edge. This is where you would see the routers sitting at the gateways. Do you see routers sitting at the gateways here? And then from gateway, it will connect to the ISP. Does it make sense? Now, another basically architecture that we have is two-tier architecture. Okay. This two-tier architecture is something like you are combining actually this core layer and distribution layer together, right? Maybe some company says, why do I have to have a distribution layer when we can do it in the, we can combine basically core layer and distribution layer here, right? So that's basically two tier where we have this, we call it actually collapsed, collapsed basically core layer or the collapsed layer. That means combining core layer and distribution layer both together, right? Core layer, and then you have similarly the access layer. In this data center world, we have something called also spine and leaf, right? But we will talk about that. That's out of scope, by the way. But just for your awareness, we have something called spine and leaf, like fabric. That's purely into the data center, right? So this is the approach. Either company will have a two-tier architecture or three-tier architecture, right? Now, what's the difference between two-tier and three-tier? I mean, if you have to, let's say, propose the configuration, right? If you have to propose a configuration between two-tier and three-tier, right? What basically you would propose? Anyone?
Cost
Like
reduction.
cost. You said cost, is that? Okay. So this three-tier is basically, I would say, the traditional model. Okay. Where you have the core layer, core switches, you have distribution switches, you have, right? On the other hand, the two-tier basically is called collapsed core, right? Where you have the node 1 and node 2 as an collapsed on the distribution layer, both have been basically combined together. The complexity wise, this two tier is lower, like complex, right? Fewer devices you have to add here to manage, but in this tier 3 you have to have managed so many devices, right? Performance wise, if you see, high, right? But limited by a single collapsed link here, right? But in basically three tier, I see the highest performance because you are optimizing heavy data center traffic. Now, if talk about the cost that you said, right? Which one is expensive? This one is expensive or this one is expensive?
Core,
Retail.
Obviously, the T3, right? Tier 3 is more expensive, and that is where you can call it that this basically tier 3 is used for, bigger deployment if your enterprise network is very big. And two tier basically you can use for the medium size of network, right? So if you have a large headquarter buildings, data centers and all, which one you would go for?
data center means we are choosing core, tier 3.
Tier 3. Yeah, the bigger network, you have to go with the tier 3. Does it make sense? Right? So that's basically the network design before, tier 2 and tier 3. Now let's talk about the wireless LAN deployment here, right? What all are the different wireless LAN deployment? So in order to understand this, oops, as you know, the devices would not be only wired, right? The devices would be also connected through the wireless, isn't it? So let me put it here, right? WLAN deployment. So in basically WLAN deployment, the first deployment that we have is the centralized. Now, what this WLAN deployment, what does that mean? This basically means all wireless endpoints, right? How would they handle? How would they be handled? How their traffic would be handled? Where would they actually connect to? See, if I have to make a small network here, right? Like if you ask me, hey, can you design me the network for wireless as well as wired, both, right? So I would simply go ahead and let's say deploy here a core layer quickly, right? And then distribution layer, and then access layer here. Now, this access layer, this is wired, right? What about the for wireless? So I'm going to put in between the wireless as well, right? And then connectivity would be something like that. The wireless would also be connected to, right? Let's change the cable color for high availability like this, right? Now, this is your access point, AP2 maybe. Let's put like this, AP3, right? And these are actually switch 1, switch 2, switch 3, switch 4, like that, right? These are distribution layer. So D1 switch, let's say D2 switch, right? This is your core layer. So core 1 and core 2. And between them, the connectivity would be like this, right? And so here, now you see AP is okay, fine. You are seeing the AP for the end devices. If it is a wire device, right, then it will connect through the cable. But if it is a wireless device, right, then it will connect through the signals, right, through the signals. Now, this access point, as of now in this network, we have only 3 access point in the design, which is okay to manage. You can access this access point and then configure the SSIDs. We'll talk about wireless fundamental and all that in later classes. AP2, you log into this AP2 and then create whatever you wanna, like authentication you wanna set and all that. But in bigger environment, if you have like hundreds of access point, don't you think it is very difficult to manage access point individually? And this is where you have something called, let me just put it in a different color. You have something called, it's connected to this, and something called WLC. WLC, wireless controller. Now, what this wireless controller is doing here, all the AP ultimately join this WLC. It is a centralized controller for all wireless. Okay, this is a central controller, centralized wireless controller, we call it WLC. All the access point would register or would join this WLC. So ultimately, you don't have to log into this AP and this AP to make change. You log into this WLC, and then whatever change that you want to make, you can make it from this WLC rather going and accessing individual APs, right? So similar technology, what we have like for all the routers, right? We have SD-WAN, isn't it? For the, let me put it here. For the routers, what technology we have for the routers? Let me put it here. For routers, we have SD-WAN, right? For APs, we have WLC. For DC, right? And then in DC, we have Nexus switches. For all Nexus, what we have? We have ACI. ACI is an APIC, which is ACI solution, right? Um, for what else? So yeah, for LAN, we have the wireless SD-WAN and DC. So similar technology. So these all are the automated way, right? Just give me a moment, guys. Okay. So I hope you guys are getting it right for access point. I'm just talking here the different solutions that we are using for different data traffic for different set of network. Like for the access point, what is the solution that we are using is controller, a centralized controller. Similarly for routers, we have SD-WAN, right? We have where we have vManage. All those routers are configured through the vManage, right? Similarly, in data center, we have all Nexus. If you have hundreds of Nexus switches, all Nexus switches are configured through the APIC, right? Which is ACI solution. So like that. So this is pertaining to this, we were talking about the WLAN deployment, right? So one deployment, basically what we have seen is this centralized deployment. What is centralized deployment? The data from users is typically tunneled, right? So we will talk about what are the different protocols, right? Uh, The centralized means all the traffic, basically user traffic, all the access point would be registered joining the WLC controller, right? And the traffic would be sent basically from user or laptop to access point, and from access point it will be tunneled basically, right? Tunneled to the WLC or tunnel to the gateway. So we'll talk about the packet flow there. But what is the use of this centralized controller? High density environment where seamless roaming between floors or buildings is required, we use actually the centralized deployment. This is centralized means it's controller based. What it is? Controller, I should say here, controller based deployment, right? Centralized means controller based deployment. Okay. This is the most common model, by the way, for large sites. All access point, as I mentioned, are managed by a physical or virtual WLC. This can be a hardware, this can be a virtualized in this centralized model. So let me put it here. All APs, right? All APs here are managed by WLC in this centralized deployment, right? The another deployment that we have, let's change the color to make it little. Another deployment that we have is Cisco SDXS. And what is this? Wireless. Cisco SDXS wireless. This is actually for the fabric, where the fabric is enabled, right? Now, this Cisco SDXS is used in a scenario where you have a multi-cloud, where you have a multi-cloud, right? SD-WAN fabric. What? SD-WAN fabric. Multi-cloud SD-WAN fabric. You know, usually this model integrates wireless directly into the wired fabric, right? So multi-cloud means you have multiple sites, right? Multiple branches here and there, right? This is basically you would use the Cisco SDXS. I would say very large deployment, large network, I should say, large network here, right? Now the control plane, obviously here, in this Cisco SDXS wireless deployment, the control plane will be WLC itself, right? Your control plane would be WLC, right? Now, because it's integration of SD-WAN, isn't it? So this is where it will be involving internet as well as MPLS, and then your traffic will be tunneled from one branch to another branch. Like this is one branch network, and this is another branch network. So in between, you have what? You have internet, let's say MPLS and internet, right? You have SD-WAN boxes here. Let's put the SD-WAN boxes. Now, these SD-WAN boxes would be connected like this, right? All this traffic would be tunneled at this through the IPsec tunnel and would be sent actually to the, so the tunnel would be like this. There would be tunnel created between this. All traffic actually would be going from this branch to this branch over the tunnel. Right? You have another deployment which is Flex Connect. Right? What? Flex Connect. This is ideal for your tier 2 and tier 3 remote nodes where a local controller is not cost effective, where you have the local switching and all. That's basically is for the branch deployment. This is basically for the branch deployment. Okay. Then you have also another deployment, which is basically cloud managed deployment. This cloud managed deployment, like you may be hearing, you may know Cisco Meraki solution. Cisco Meraki solution. Right. This is also a cloud managed deployment. Right? Cisco Meraki or your cloud-based SD-WAN as well. Right? So there are different, these are the different wireless deployment in out of which what you would see this as a common, very common, I would say. This you would see as a common deployment. Okay. This you would see as a common deployment for the wireless controller or WLAN deployment. Any question from this? So this is all basically the introduction of how basically tier 2 looks, how tier 3 looks, right? Where the components are fitting in the network, right? Whether it is wireless, whether it is wired. This is what we are talking about, how the availability you should achieve. Okay. The next thing, let's talk about the basic routing flow. If you don't have any question, right, then let's talk about the basic routing flow. Now, in order to understand the flow, let's take one scenario here. So first of all, we all know what is basically routing and uh, different types of routing and all that, isn't it? What is routing? Anyone?
Router. The router is connected to different
No,
different.
what is routing? Router is fine. What is routing?
Routing is a process of forwarding the packets based on the destination IP address.
So if this PC, okay, sends the packet to this PC, is it called routing?
No,
Why? Why this is not called routing?
because that is internal IP. I mean private IPv4 configuration.
If it has the public IP, then if this PC has a public IP, this has a public IP, then
No idea.
right. So routing, who does the routing, by the way?
Router and multi-layer switches also.
Any layer 3 device, any layer 3 device can perform routing. Do you agree? That device can be router, can be multi-layer switch, can be PC. Computer is also layer 3 device and it can also do routing, just for your awareness, right? firewall. Any layer 3 device can perform the routing. Now, because in this example, PC is sending the packet to this PC, the question is, will the packet go to router?
Yeah, obviously.
No, hold on. Between this PC and this PC, if the PC communicates with this PC, will the packet go to router?
No,
No, it would not,
the
right?
packet
Because
will go from switch
it will go
to,
to switch and switch will send it here.
yes,
This packet would never go to the router. So you said that routing is a process of sending a packet, right? From one source to destination. This is source
Yes.
and this is destination, but this is not called routing. Routing is a process of sending packet from one network to another network. This is what you missed. Is it making sense?
Yeah.
So from one network to another
yes, we
network?
are connecting some different network.
Yeah,
Yes,
because who connects to two different network? Which device connects?
router,
Router would connect, right, to different network. Your multi-layer switch like layer 3 switch would connect. Firewall can connect two different network. Two different network means here in this network, in this design, you see here you are running 192.168.1.0, or let's like this. Here you are running 192.168.1.0. Here you are running different network. Here you are running different network. So do we need router? Yes. I don't need router if this PC, if you don't have to send the traffic from this network to this network. If these PCs are communicating within the network, I don't need router at all. Okay. But yes, I need router when the traffic you are sending from this network to this network or to this network. Then I need a layer 3 device. Do you agree?
Yes.
yes,
So routing is a process sending packet from one network to another network, right? There are two types of routing, IP routed and IP routing. IP routed is fixed. Fixed means it's a transport. For transport, we are using IPv4 or IPv6, right? On the other end, what is IP routing? IP routing is a finding out the path, destination, right? IP routing is a process of finding out the destination. And in case if we have multiple paths to reach the destination, finding out the best path, right? Now, how would it do? It would use obviously the different routing protocols and all. Right. So IP routing, we have static and default routing, and then we have dynamic routing, right? So this static and default way routing, you do it manually. And in dynamic, you take the help of routing protocols like RIP, PIGRP, OSPF, ISIS, right? BGP to advertise the network automatically. Okay. But here, let's understand if this PC, let's create a scenario. The scenario is this PC wants to talk to this PC3, where the MAC address of this PC is PCPT, right? MAC address of router is router 0, let's say. This is PCPT MAC address 1. Okay, these are the MAC addresses. MAC address A here, MAC address BB here. Now, let's say you want to send the packet from this PC0 to PC3. What will be the flow? Anyone?
yes.
Yes, please go ahead.
The Ethernet frame is reached to switch. The switch is broadcast. The switch is sending the information to router. So router to exchange that BB
What
interface.
what
Yes.
Ethernet frame?
Yeah, PC will, for example, the PC0 is communicate to PC3. I mean
Mm-hmm.
different network.
Mm-hmm.
So the Ethernet frame will send to switch.
Who would send the Ethernet frame? Will the Ethernet frame will be sent automatically, or you will send, you as a user?
Yeah, I am only creating that.
Okay. So you are creating what? So you are sending the packet. What packet you would send? Ethernet frame?
Yes,
So in order to send the packet, you should have a packet, right? Let's say what packet you have, whether you have email or you want to check the connectivity. So maybe you are sending some ICMP, right? Or you
yes,
are sending some HTTP traffic as a user, isn't it?
yes.
Let's say you are sending ICMP.
Okay,
Let's say you want to check the connectivity between PC0 and PC3. Okay, how would you check the connectivity? Using the ICMP protocol? I have written here ICMP, right?
yes.
Now can you tell me the flow?
Yeah, now I can ping that IP address here to there.
Okay,
So what happened? The ARP will send that request to switch. The switch will broadcast. If it is same network, it will ping.
okay, so does ARP happen every time?
No,
Then you started with the ARP, so does ARP happen every time?
no. Once it is connected, once the MAC address will land means it will unicast.
Mm-hmm. Yeah, go ahead, go ahead.
So the packet will go from here to switch is sent to router.
Okay,
This router will check the path. I mean,
for
uh,
for ARP.
yes, or
Okay,
then the router will check the path, like which interface is configuration in another network.
okay, this interface.
Then the packet data IP packet is forward to router.
Mm-hmm.
Then router will send that to switch to then PC.
So this is first step, second step, third step, and
Fourth step,
uh, fourth step and fifth,
fifth
fourth
step.
and fifth, right?
Yes,
This is what you're saying.
yes,
Okay. So let me correct you for here. First of all, okay, let me just remove this. So first of all, since you said ARP, let me put it here, okay? ARP works within LAN. It never crosses the LAN, okay? So yes, ARP would go from here to router, but router would never send that ARP to another router because that's one broadcast domain. ARP never crosses the broadcast domain. Is that clear for you?
yes,
Right? So what you said here, ARP will send our router will send our ARP to router 1, which is incorrect. ARP will stay till here. ARP works within the LAN means within the broadcast domain, I should say here. Broadcast domain. I hope it is clear, right?
yes.
Yes, Sudarshan, you were saying something. Can you tell me the flow? Sudarshan, are you there?
Yeah, am I
Can
audible?
Yeah, you are audible. Can you tell me the flow?
First PC sent to the
Sorry, yeah, go ahead.
yeah, first piece is sent to the packet to the switch forward to the router, and router 1 to router 2 it goes to the packet, and it will reach to the switch to and PC. Here the thing is main, PC does not know the uh, like PC3. like source address, destination address, it does not know the PC1. The time like switch can learn the MAC address.
No, I'm not understanding, Sudarshan, what you're saying. So you are sending the ICMP packet, right? From
Yeah,
PC0. Yeah. From there, can you start
PC0 send the ICMP packet to the switch.
to switch?
Yeah, switch can find the source IP or like destination IP.
Okay, leave it. So guys, this is where I said it is very important, very, very important, this flow. Okay. And if you are able to answer this correct, right, think that half of the interview you have passed. Because this actually tells interviewer that how deep knowledge you have in your routing and switching concept. Okay, okay. So let's focus here and understand it properly. Okay. Because if I am an interviewer, I want to hear step by step process. Okay. Let's say I say that PC0, I open a command prompt and type ping, right? An IP address of this PC3, which is ping 192.1.0. Let me put it here. What I type? CMD ping 192.168 2.3. Where CMD, open command prompt and open CMD and type this. Okay. What happens after that? This PC0 will try to interpret ping command because ping is accessible. This PC0 understands what ping command is, right? Ping, it knows that ping means I have to immediately involve what? ICMP protocol. In ICMP, there are two messages. What two messages? ICMP echo request and echo reply. Do you agree?
Yes.
So this PC0 knows that, okay, I have to send ICMP echo request to this guy. Which guy? This guy. Hold on. Does PC0 understand? Does PC understands this value? This is a decimal value. It doesn't understand it, right? And that is why this PC will convert what? It will convert decimal, convert this IP from decimal to binary. Okay. After conversion, because it understands binary. Why that is why it is converting, because it only understands binary, not decimal, not numeric value. After converting into a binary, what is next? Yeah, what is next? That's the first thing. So first thing what happens is PC0 interprets ping command. Okay, that's the first. Fine. Then what? Then second, it will involve ICMP. That okay, because I have it is ping ICMP echo request. Third, convert this value IP address from decimal to binary. What is fourth? Compare source binary source. I'll put smaller source and destination binary. What does it mean? This PC will compare its own IP, which is 192.168.1.2 with the destination 2.3, and then check why it is compared to see whether it is in the same network or same or different network. Different network. To okay, it will compare source and destination to see if this destination is in my network, which is this network, or different network. Obviously, when it compares, this binary will be different from this binary, isn't it? This is where PC0 knows that, okay, this destination is not from my network, it is from outside. Cool. Outside this information, in this fourth step, it has understood. Fifth is, now it will start building the packet. This fifth. Build a layer 3 packet. Because ICMP, ping is layer 3, right? That is why it will build a layer 3. ICMP is layer 3. So immediately it will add IP header. Now I hope you guys are network engineers. You know what is IP header. If no, my request would be, suggestion would be to go through th go through IP header. Okay, there is video that we have uploaded in our YouTube channel. You can understand it well properly there. So go through IP header there. Understand each and every field of it. Okay, it will add IP header. The main thing in IP header is source IP, destination IP, and obviously TTL as well. That's basically IP header, because source IP, it knows I am 1.2, destination IP, it knows what 2.3 or 2.2, let's say here it is written. So 2.2, let's say PC0 communicates with PC2, okay, which is 2.2. So destination IP 2.2. Layer 3 is complete, yes or no? This layer 3 is completed because it has all required information. Good. The next step is sixth. It will add layer 2 because it will send the data like this. What? Network layer, from network to data link layer, and then from data link layer to physical layer, like this. So network layer added. Now it is adding the data link layer. In data link layer, what we have? Ethernet frame. What are fields we have in Ethernet field? Ethernet header, if you're not aware of, and Ethernet header. Go through it. Okay. IP header and Ethernet header. So here we have source MAC and destination MAC. What we have? Source MAC and destination MAC. Now, the source MAC is what source MAC is? PC0. This is the source MAC. It has got it because it knows what is my MAC address. Now let's talk about the destination MAC. Does it know what is destination MAC? Anyone?
We don't know.
It doesn't know, right? Why? Because the destination is obviously different network. It would not be knowing. But the question is, as soon as it identifies that this is the different network, it will check, do I have a default gateway configured, right? So now in order to know the destination MAC, what it will do? ARP. This is the seventh step here. What? It will perform the ARP query. Now you know what is ARP, right? What is ARP, Sudarshan?
ARP is a translator between the IP address and MAC address for LAN communication.
Translator. Why translator means? Can you
Uh, like uh,
elaborate?
like translator between IP address and MAC address. It can convert, right?
Ramesh, what is ARP?
Yeah. ARP is a address resolution protocol. It is used to get the destination MAC address. I know source MAC address, and I don't know the destination MAC address. I know the source IP address, but I know the destination IP address.
So Sudarshan, this
But
translator is not a correct word. Okay. So mind what you are saying, reframe it, and then make a note of it. Okay. So
Okay.
ARP is a protocol that learns MAC address with the help of IP address. I have written here. It learns MAC address with the help of IP address. Simply, I have IP of destination, but I don't know what is the MAC address of it. This is where I am going to use ARP because there is ARP header also. This is ARP header. You see that? Now this PC would send, let me put it here as a 8. This PC, it will use ARP and send ARP request. In ARP request, it will add, okay, I am 1.2 source IP. My MAC address is PC0. Destination IP. Why destination IP here 1.1? Because I just now told that this PC will not be learning the MAC address of PC2, which is 2.2, which is different network. It will be learning the MAC address of its default gateway. Now, here itself, what if the default gateway is not configured? Let's understand the scenario. No gateway. No gateway. Then what? Immediately the ICMP packet would be dropped here. If no gateway, as soon as, in which step it will be dropped? In the fourth step itself. It would not even send ICMP. It would not even use the L3 header. Immediately it would be dropped because it knows that, okay, the destination is in different network and I don't know who is my default gateway. This PC needs to know my default gateway if you are sending the packet to outside. Do you agree? So no gateway, drop the packet immediately. Now let's say the gateway IP is 1.1 that you have configured. Okay. So if it finds its default gateway, then it will go through the rest of the process 5, add L3 packet, 6, L2 packet, then send an ARP. ARP will be sent to its default gateway. And this is the format: ARP request, source IP, destination IP, source MAC, and destination MAC. What is this destination MAC FFF? Because this PC does not know what is the destination MAC address, because it is learning destination MAC only, right? If it doesn't know, how can it put it? So it doesn't know what is destination MAC, and that is why instead of that it is using FFFF. This is the layer 2 broadcast address. 12 times FFFF means 48 bits. This is the ARP request. Is it clear?
Yeah.
If you have any confusion, go through this video again and again. Note down if you have any question. Ask me that this part I didn't understand. We will discuss it. But I want this concept to be clear. Cool. ARP request is sent from now because this PC is connected to switch. It doesn't know, by the way, but since obviously the signal would be sent out of this interface wherever it is connected, and finally it is connected to PC. Sorry, it is connected to switch. Now switch is in an intelligent device. Switch has a 3 function. Remember it here. Switch has a 3 function. As soon as it receives any signal, okay, what all I'm saying every time. address learning, address forwarding, and preventing loop. These are the three functions. What is address learning? Learn sender MAC address. So when this overall, this ARP request is sent to the switch, switch will open which header? Switch is a layer 2. Layer 2 means data link layer. In data link layer, what we have? Ethernet header, right? It will open Ethernet header and check source MAC, which is PC0, and destination MAC. So PC0, so when it checks the source MAC, now the switch knows that, okay, there is a MAC address connected on my this port. This port may be, let's say, F0/1. There is MAC PC0 on this. Address learning, where will it keep it? It will keep it in CAM tables, which maintains a table called CAM table. What is the full form of CAM table? Content Address Memory. By default, when you add a new switch, all that entries are empty. But as soon as switch receives the signal, it starts learning that MAC addresses. So it now learns that, okay, MAC address PC0 is connected on F0/1 here with the VLAN ID 1. By default, all the port are with the VLAN ID 1 by default, unless and until you change it. So that's the job of address learning. It will learn the address and keep it in CAM table. I hope this is clear.
Yeah.
Okay. Second function of the switch. What? Address forwarding. It has learned the address, kept it in the CAM table. Next function is forwarding. It has to forward. To forward, it will check what is the destination MAC, and destination MAC is broadcast. Now what switch will do? Anyone? It will broadcast to this port as well as this port. This is called known broadcast. What do we call it? Known broadcast or flood. There are two types of broadcast: known broadcast, unknown broadcast. Known means it knows that this is a broadcast message and I have to send it to everyone. Unknown means when it doesn't know, but still it has to send. So it will send a broadcast message or broadcast here and as well as here. This PC1 will receive. PC1 knows, gets to know MAC address of .2. It will also update its ARP table. What table? ARP table, right? When router receives, who will reply in this network now? Guys,
The packet is dropped.
no, who will apply here? Who will reply?
Router.
Why? Router?
Because here different networks, right?
No. Yes, router will reply because router is the destination IP 1.1. Router is the default gateway. You see that destination IP.
Yeah, 1.1.
Who will reply? The one is configured with 1.1. Who is configured in this network with 1.1? This router.
Yeah.
So this router would reply ARP reply and saying, hey, my MAC address is whatever MAC address you have. Let's say router 0. Right? When that ARP reply is sent to the switch, again, what switch will do? Anyone? What is the first job of switch? Address learning. It will again open Ethernet header and check the MAC address. Okay, routers, and update that MAC address router 0 on this port. Let's say this is F0/2. So it will update saying, okay, F0/2 has MAC address R0. Second, address forwarding. Now, this time will switch send broadcast or unicast?
Unicast,
Why unicast?
because the destination MAC address is land in a
Yes,
router.
because router knows that I have to reply to the PC0 MAC address. So switch knows that, okay, PC0, the destination MAC is what? Source MAC is this and destination MAC is PC0. Switch knows that PC0 is on which port. How does it know?
It's land in port MAC
From
address.
this CAM table.
Yes.
From this CAM table, it knows that the PC0, which is this guy here, this PC0 is connected where? This port. Which port? 1. And it will send a unicast packet here. Now finally this PC0 knows the MAC address of its default gateway and add it here. That the MAC address of 1.1 is router 0. Now this information is complete. Layer 3 as well as layer 2. Now it will send ICMP echo request. It will be sent to switch. Switch knows that source MAC destination MAC router 0 is on the port number this because it has updated it. It will send it to router. Router. Okay. Now this router, when it opens, when this router receives the ICMP echo request, what router will do? Anyone?
Router will check the destination
How will it check?
routing table.
No. How router will know that destination is 2.2? For that, it will open the layer 3 header, right?
Yes.
So
Layer
router, when it receives ICMP, it will open the layer 3 header. In from that layer 3 header, it will check source IP is 1.2. I have to send that packet to 2.2. What next? Now router will check, do I know this 2.2?
yes, router no.
How does it know? It will check
Because
its RIB table, which we call it routing table.
yes,
Routing table.
table.
In this routing table, if the 2.2 is there, let's say in this routing table, if the 2.2 is not there, then what will happen?
Packet will drop.
Router will drop the packet.
Yes.
And because ICMP is a protocol, ICMP will generate a message to this PC0 saying, hey, reply from 192.168.1.1 destination host unreachable. Have you seen this message?
Yes.
Yeah.
Cool. Let's say now another scenario, there is entry in this routing table, then obviously it will send it to routing. So it will check who is next hop IP. Next hop IP is, let's say, 150.1.12.2. What router will do? Anyone? Router will create layer 3 as well as layer 2. What would be layer 3? What would be source IP? Here,
Source,
when router 0 is now sending the packet to 2.2, what will be source IP?
source IP is a router interface IP.
Means here 150.1.12.1.
1, 12.1,
Okay. Destination IP
12.2.
12.2. No, it's wrong. Keep it in mind. Layer 3 never changes. Layer 3 would remain same. It will change only when you are using NAT, network address translation. If you are using NAT here, then only the source IP would change from 1.2 to 12.1 or whatever address that you're translating to. But if no NAT, then this would remain same. This detail would remain same. Source IP would remain 1.2, destination IP would remain dot 2, 2.2. What about the layer 2? Source MAC would be AA and destination MAC would be BB. So MAC address will change, but IP will not change. Is it clear?
I mean, you are trying to explain like that interface is directly connected to router to learn only MAC address. It's not learning IP address, correct?
I did not get what you're saying, Ramesh.
The MAC EAA, that interface is connected to BB,
Yeah,
right?
this is the LAN interface.
Yes.
If router is sending the packet over the LAN interface, then it will add source MAC as its own MAC address.
Yes.
Destination MAC, because it knows that the destination next hop IP is 112.2.
Yes.
Again, if this router doesn't know what is the MAC address of 12.2, what it will do? Obviously, it would not be knowing first initially, right?
Yes.
Then what it would do? Same, this process.
Okay.
Which
So
what
router will
process?
generate
Hold on.
that or
Yes, router will generate ARP here and learn the MAC address of 12.2. This router will reply with its own MAC address saying my MAC address is BB, and this is where it will add source A and destination MAC as a BB and send that packet to R1 here, from here to here. Is it clear?
yes.
Now this router 1, when router 1 receives that packet, again it will open the layer 3 header, will know that I have to send it to 2.2. Okay, this would remain same, but this would change. What would be source MAC here? Source MAC would be this router MAC address, let's say R1. What would be destination MAC? If this router does not know what is the MAC address of 2.2, it will send ARP, and with the help of ARP, it would learn the MAC address of this PC2 and then send it. Use that PC2 MAC address. I hope this is clear, right? And finally send it to switch. Switch will do the same 3 functions and send it to PC2. This PC2 has received what? ICMP echo request. Now this PC2 is supposed to send a reply, ICMP echo reply. Okay, ICMP echo reply. When it sends the ICMP echo reply, who will be source?
PC0.
Let's say source IP. What would be source IP? Source MAC, destination MAC. Yeah. What would be source IP? PC2 is replying, right? So now PC2 is the source. What is the IP of PC2? 2.2. Destination IP 1.2. Source MAC, its own MAC address PC2. Destination MAC, router 1. And then send it to router 1. Router 1 would again follow the same process. Open layer 3 header, check source IP, destination IP is, this router 1 has to send the destination ICMP to destination 1.2. It will check its routing table. If the routing table entry does not have this in IP, it will drop it. ICMP will generate a message request timeout here. If it has that IP, then it will send it to next hop IP. After the adding the source MAC destination MAC, when this router receives it, it will send it back to this guy. Same thing, same process. How it took to go outside, the process which was used to send that packet outside, right? The same process would be used to receive the packet. So that is how, this is what it is called, the IP packet, IP flow, packet flow, as well as basic switching flow. The different switching, the function of switch. So any question from this?
No.
Okay, but I will have the question. I will ask question. Okay, so better I'll share this recording with you guys. Go through it, note down the question, and then let me know if you have. If you don't have, then I will ask the question. Cool. That's it
Okay.
for today. We will connect it tomorrow. Thank you for watching.